Hello, my name is Brandon Wade. My partner is Stefan DeSlate. Welcome to our ece196 hardware project presentation. Our motivation for the project was twofold. With the emergence of smart home devices in the last decade, we wanted to take a shot at building on our own, incorporating functions found in other standalone devices such as smart locks or Alexa automated devices into a single functioning device for less than what it would cost the average consumer. With regards to our system and the initial cost of the Raspberry Pi platform, the more smart devices managed by the Pi itself, the higher return on investment and savings one can accumulate. Having not previously worked on a Raspberry Pi, we wanted to try implementing a broad range of capabilities and then design the system to be flexible for future expansion. Our goal was to build an Alexa-enabled window curtain with the system centered around the Raspberry Pi platform, enabling communication with Amazon's Alexa Echo product line. The device would perform the following. It would allow for voice commands to open or close curtains through Alexa. The system would be designed to automatically open or close based off of sunlight, or even after a set timer once a certain amount of sunlight has been measured. Uh, Security features would include, upon failure to unlock the front door via facial recognition, the window shades, curtains would automatically shut if not already closed. This project was a proof of concept due to the requirements for more powerful motors to pull the heavier curtains. The parts used for this project include the following. The Raspberry Pi itself is the center platform, a photoresistor, a 220 ohm resistor, a 1 microfarad capacitor, and a red LED. We have two stepper motors coupled with a L293D motor driver, some tools and materials for platform construction, including 3D printed parts, the Raspberry Pi camera, the Tower SG90 servo motor used for the locking mechanism. Here we can see how the project was wired. This wiring diagram was realized using the widely popular fritzing software available for free on GitHub. If we look to the right, we can see the motor leads are wired in parallel to the L293D motor driver. We also have a red LED indicating the position of the curtain as to whether it's either open or closed. This is strictly for testing purposes. If you examine the Raspberry Pi directly on the diagram very closely, you can see the Pi camera is attached via the ribbon cable camera port on the Pi itself. Here's the schematic of the wiring diagram from before. We want to note that the schematic does not show the Raspberry Pi camera being connected. Here's an illustration showcasing the design of the curtain motors. The black lines represent the curtain rod itself. The sundial pictures represent the curtain motors / pulleys. The motors are connected to each other via a red strap and collectively open or close the curtain by means of a fixed mount represented by the black ring connected on one side of the curtain. Pictured to the right is the proof of concept model. In order to minimize costs, I repurposed some old prescription bottles as motor pulleys and some 1-inch red strap that I had lying around. The black Velcro represents the junction where the strap and the curtain would be connected. When the pulleys move the strap to the left, the attachment point represented by the Velcro strap or wrap would pull the curtain in the desired direction. In order to achieve our design goal for the curtains, we started with the basics of each individual part. We've made use of the tutorial links provided below, highlighted under tutorial. Forgive me. We were able to develop our understanding of the individual components necessary to complete the objectives of the project. The links below were comprehensive, providing wiring diagrams, test code, as well as all instructions for Python package installation and guides. Both the photoresistor and the stepper motor tutorials ran without issue. After success with both the stepper motor and photoresistor tutorial code, we proceeded to combine and make the necessary changes to have them working in tandem. This involved a basic understanding of Python, package installation, as well as design choices, with all but the latter being covered in the tutorial. The next in line and step was to start incorporating Alexa functionality. Amazon has had great success with this Alexa Echo product line, and part of their success can be attributed to how relatively user-friendly it is to develop for, especially with somebody with modest coding experience. One needs to set some parameters for communication between the Pi and Alexa, and proceed to upload a JSON file for the desired skill creation. This is where the skill is defined, as well as the commands spoken for Alexa operation. This is highlighted in the tutorial linked before. We made a few necessary changes to accommodate our desired results. This was a little bit harder to implement when compared to previous two tutorials, as it required some troubleshooting beyond the scope of the tutorial code itself. Following the tutorial guide linked to the left, we encountered a common Python package compatibility issue. Reading the comment section of the tutorial itself, we were able to identify the problem. These issues were rectified by installing the cryptographic package 2.1.4 and using the following line of code shown below. I would recommend to any users encountering issues with such guides, make a habit of glancing over to the comment section prior to their first attempt in order to be aware of potential hurdles and to not revert to full-blown panic mode when prompted with a list of errors in your Python terminal. Once the fixes were made, we were able to successfully instruct the Raspberry Pi to open the curtains via voice command or via text via the Alexa developer console.
After successfully implementing the sunlight detection functionality, curtain motor scripts, as well as Alexa functionality, we shifted our attention to the locking mechanism and facial recognition function. The tutorials, like before, were very comprehensive. The servo motor tutorial was very similar to the stepper motor tutorial and was rather plug and play, as was the camera setup. However, the facial recognition required more setup. But before we get into that, let's examine the locking mechanism design and setup. For the lock, I was able to build it using a servo motor. And instead of designing the 3D model for the lock myself, I looked up on Thingiverse and found a good model for the lock that would include the servo motor, the way I thought of it to be used. But for a more heavy duty application, you can find an electronic door strike that would also work well. The top photo is the original model I downloaded from Thingiverse. However, I had only the micro servo motor, and so that wasn't compatible with the model. And after learning how to use the basics of Fusion 360, I edited the model to fit the micro server. The final print still didn't fit the motor well enough, so I ended up having to break it down and tape the motor, which you'll see in the demonstration video. I was also able to use a facial recognition library that I took from GitHub. And the library applied a support vector machine algorithm for machine learning, which is commonly used in classification. And in here, we're classifying different faces. So to save a profile, we would have to add the photo of the person to a folder directory. And the face in the video feed is encoded into a matrix and compared to the profiles using the library. We then set up a local network server where the camera feed will be hosted using Flask. And the feed is then embedded in the HTML page. Using the HTML buttons and Python code, we can access the motor that controls the lock to open it or close it.
At this point, the stage is set to bring everything together in full scope. Using threading, we were able to combine individual scripts running the functions of each piece into a single script. A single script was chosen to act as the main For functionality, we chose the Alexa script. Each remaining script was rewritten as a function and then called on its own thread using the following command in the main. The system communicates via a global variable acting as a status flag for the state of the curtain, whether it be open or closed. Our preliminary results for the proof of concept came out really well. With regards to the project goals, we were able to successfully integrate the sunlight detection feature, working in unison with the Alexa voice commands, operating on the curtains, using the threading process described on the slide before. With regards to the facial recognition software and the lock mechanism, we were able to unlock the lock via the facial scan. We were unsuccessful in implementing the final feature, whereby upon failure of reading a face, the curtains would automatically close. We are positive that this can be achieved, and we just attribute this to time constraints and the troubleshooting we've had during remote learning. We are confident with enough time, our project can be fully realized. When considering realizing the full-scale model, here's some things to consider, including some challenges and design choices we'll have to make. We would need to spend some time determining the motors and required torque to pull the curtains of large size. And this will likely require separate power supplies for the motors. However, we've already found a way that we could run this system with a single motor. With the increased power requirements of the curtain motor stepper motors, we might also need a more robust motor driver. We would need to finalize the software for any undiscovered or undisclosed edge cases we haven't already taken care of. And we would also need to determine the mounting hardware required for the certain curtain motors. We'd have to spend some time fine-tuning the sunlight detection. And we will also want to generalize the device with compatibility of multiple curtain types. We believe we've mostly conquered this issue by means of a simple strap with the simple Velcro strap, but aesthetically speaking, it's not very pleasing. And then lastly, we would want to increase the performance of the facial recognition. We'll now take a minute to demo the product. Here we go.
Start off with our curtains right here. And I don't have an Alexa right now, so I'll be using Alexa. And when the LED light is on, that means the curtains are currently open. So I can go ahead and tell Alexa to close it. And so this shows that the blinds are closing and the LED is going to be turned off. Now it's turning off, and then if I try to close it again right here, it won't close because Alexa says the curtains are already closed. So go ahead and open it again. Like telling Alexa to open the curtains. And no, so the curtains are now being opened. And the LED is on, so we'll try to open it again. And we should expect it not to continue unraveling because it's already open. And so there's also some photo sensors here. So if we cover this up, and it'll automatically close. All right, so this is the facial recognition aspect of our project. Over here, we have the camera feed, and you can open it up using your IP address. And so right here, I'm going to point the camera towards me, and then it recognizes me as Stefan, so it's working as intended. And if you can see that we have two buttons right here, there's a red one and a green one. And so I'm going to press the red button right now. And so when you press the red button, then you can lock from lock whatever you need to lock from the website over here. And I'm gonna press the green button. Yeah, it unlocks it.
Thank you.